So I will talk about variational Landau-Zener-Stückelberg. I will explain what Landau-Zener-Stückelberg is and how this can be used to very explicitly exploit the coherence of a diabatic quantum annealing device. And this is actually very much, this project is very well placed here at INQA, because it all started actually on April 25th in an INQA seminar where Jeremy was presenting this paper here, diabatic quantum annealing for the frustrated ring model. And what the authors did in this in the work is they tried to find the ground state of the frustrated Ising ring. And the frustrated Ising ring is kind of like a very nice testbed problem, because it's technically speaking not a very hard problem, but it has an exponentially closing spectral gap. So for an adiabatic device, it would be like a very tough nut to crack. And what they did in their work is that they said, okay, we do kind of the traditional annealing approach, where you start in the ground state of the transverse field Hamiltonian and then interpolate towards the problem Hamiltonian, such that you hopefully end up in the ground state. What they changed now, though, is that they this interpolation function, or the schedule, here they call it A, was optimized variationally. So they chose like a very large ansatz class of functions, and then iteratively optimized the parameters of those schedules. And then what they find is that if you do this, then actually the optimized schedules have a runtime that is polynomial, or actually even quadratic, despite the minimal gap closing exponentially fast, which is what would limit which would give you the runtime if you were just to run like a linear schedule, which is like this exponentially increasing runtime over here. And what they noticed.
Quick question, sorry.
Yes.
So if it's optimized time, does that include the optimization time?
No.
Okay, fine.
But in the very end, I will come back to that concern. So what they find, however, is that the optimized schedules, they always have like this wavy type of shape. Those are the schedules here plotted for various problem sizes. But apart from a few outliers, always they kind of go up and down, and then only then they cross through the minimal spectral gap, which is here denoted as like this A star here, which is very close to the end. So essentially, they do some sort of, like all the optimal schedules do some sort of wiggle and then go fast through the minimal gap. And was kind of left as an open question, what's like the working mechanism behind this? And or even why these schedules look like this. And what I will basically spend the remaining time of this talk is, or what I will try to do, is to propose a solution or an explanation why the schedules look like this, and propose a way how this can then be used for other problems in a hopefully slightly more efficient way. So one thing to notice is, while it is very natural to look at the minimal spectral gap when looking why an annealing algorithm works the way it does, actually we suspected that the actually interesting part is kind of here in the middle somewhere, right? So that because this is kind of where the system goes several times, right? It goes beyond this time and back again, and then for the third time through this center line, right? So the question is a little bit, okay, is there anything interesting happening at this red line here? We all know that, okay, the minimal gap is obviously an interesting point, but maybe this point in the middle here, like halfway through the anneal, let's say, maybe this is interesting too. And this is kind of where our previous work had like something to say about it. So maybe let me quickly summarize. It's a work that we did mainly last year. It is on arXiv and soon to be in PR research. And for more details on this theory, you can refer to that. Although it's actually not the main focus of this paper. It's just kind of like a side point. But essentially, in the standard adiabatic quantum annealing scheme, where you interpolate between a driver Hamiltonian and a target Hamiltonian. Typically, you choose the driver Hamiltonian in a way that the ground state is delocalized, while the target Hamiltonian is typically localized, so it's like some bit string or some Z eigenstate, let's say. So you start out in a delocalized state in this basis, and as you anneal, eventually the system has to localize. And if you're lucky, it localizes directly onto the optimal solution, which has some very nice, or not necessarily very nice, but nicer properties in terms of how the gap is scaling and so on. But often you are not so lucky, and actually the system localizes in a local minimum, which means it's kind of assumed, or the ground state is very close to like a Z eigenstate. However, it's not the Z eigenstate that is the optimal solution. And then later on in the anneal, there needs to be some tunneling, and this tunneling is what takes a long time and makes the gap very small. And the frustrated Ising ring problem is essentially one of these. Is a problem of the ladder persuasion. So the delocalized concept first localizes it in some local minimum elsewhere, and then later there needs to be there's like some avoided crossing, which makes the gap incredibly small. And so maybe let's consider or pay some little more attention what actually happens at the center point of this, or in the middle of the annealing path, right? So you start out. This is like a very simplified graphical, or like a very simplified way to get like some intuition on what's going on in the annealing path. So what we plot here is like the energy up to first order perturbation of the delocalized eigenstate, or of the delocalized ground state of the initial Hamiltonian, while in the end we have up to first order perturbation the energies of, or some cartoon of energies of the state that's localized in the global minimum and the state that's localized in the local minimum. But these three lines already tell us or give us some intuition on what's going on. Namely, in the beginning of the anneal, we summed in the delocalized phase, where the instantaneous eigenbasis is close to the eigenbasis of the driver Hamiltonian, which typically is then extended in the computational basis. And as you anneal, eventually there's like some sort of a critical region where the eigenstates undergo some sort of transition, and they after that type of critical region, you end up in the localized phase, where the eigenstates are close to the eigenstates of the target Hamiltonian, right? And in the middle, obviously, in this localized phase, this is where then the avoided crossings can happen, and these are the crossings that get very small and which you would like to avoid. And our hypothesis was now the optimal schedules that Jeremy and his collaborators found, they sweep several times through this phase transition in order to populate the first excited state, which then allows them to not care about the minimal gap anymore and just go fast. So basically they sweep back and forth around this area here, and then allowed to go fast through the exponentially closing gap. And there is some evidence of that in the data from their simulations. So this is a plot that is a slightly modified version of what they had in their paper. But if you look, for example, in the first row, it's on the left are almost the optimized schedule, and then for comparison, the linear schedule on the right. And the respective schedules are shown in the dashed line in the background here. So linear is just the ramp, while the optimized schedule is like this wavy shape. And the colorful lines, what they show are the populations of the instantaneous state of the system, or the current state of the system, in the instantaneous eigenbasis. So in the beginning, the system is pretty much in the ground state, and then you sweep once, and it kind of puts half the population roughly remains in the ground state, and half goes to the excited state. The sweep again, where it's not that much happening on the second sweep, but on the third sweep, and basically all the population transitions to the first excited state, or the instantaneous first excited state, which then, after the minimal gap, very rapidly turns into the ground state. And this is then how they find the ground state. And our claim is now, okay, these sweeps, they kind of go back and forth between the localized and the delocalized phase. And this can be seen if you just plot the participation ratio of the ground state, right? So it's like in some number that is close to, or pretty much 1 if the ground state is extended, and it's exponentially small if the ground state is localized in the basis. And indeed we can see that it starts out in an extended ground state, then in the first sweep it localizes, but then goes back into like an extended state. So indeed, like these sweeps, they go back and forth between those two phases. But how does this now help to, or basically, yeah, they're sweeping through this transition, but how is now this precisely helping to populate the first excited state? And to that end, we must take a brief step back and remind ourselves of the Landau-Zener model. Landau-Zener is like a two-level system where essentially you have ground state and excited state of where the energies vary, and they are coupled by like some typically very small off-diagonal element, right? And you can kind of see the graphical depiction here, right? And if you linearly, or basically this is like the spectrum of this two-level system as a function of like these diagonal elements. And as you sweep the diagonal elements from -1 to 1, so they kind of just change the order actually, you get like a very, very minimal gap here in the middle that kind of is the size of the delta on the off-diagonals. And if you sweep through this minimal gap at like some rate v, like some sort of velocity if you will, then the Landau-Zener formula tells you how much of the population will be transferred to the excited state, right? And essentially you can think of that as, or if you assume that the system initially is prepared in the ground state, then after one sweep you will end up in a state that where the amplitudes are then chosen according to these population probabilities, and naturally you will also pick up some phase. But what happens now if you do these sweeps twice? So you sweep once at some velocity v1, and you sweep it second time for another velocity v2, and in between you, for example, you would just do nothing for like some amount of time. You just wait. Then you basically, if you do kind of the calculations, what happens to the state that was initially in the ground state, you end up with a slightly more verbose expression here, where the P1s and the P2 are just like the transported populations for each sweep. As well then some phases here, phi1 and phi2, but also some phase W. And this phase W is acquired due to this waiting time here. And actually, you know, if you look at the expression, then if you just wait for a different amount of time, then you would kind of get some periodic interference pattern, right? Because if you just keep everything fixed and only wait for longer or less time, then only this part here would be kind of rotating, let's say. And this phenomenon is called Landau-Zener-Stückelberg interference, and it's actually, yeah, if you think of this system of a ramp and a weight and another ramp, it's actually very, very closely related to interferometry with some beam splitter, right? And like in interferometry, you send some light wave, let's say, into like one of the channels, and you could think of it as a beam splitter that kind of splits the beam in half. And now these two paths of the light beam, they are of different length. So the one wave will pick up a phase, and then if you recombine them and look at them, you will see like a periodic interference, or you will see like a periodic pattern in the intensity that depends on the phase that you pick up due to this path length difference. And basically this path length difference here is just in Landau-Zener-Stückelberg interference, it's just like the waiting time here. And if you calculate these numbers, then depending on how much population you transfer, which in the interferometry case would be depending on how much you keep in each side of the beam, you can then either just see like a little bit of wiggle in the ground and excited state populations, or if you kind of split the beam in half, then you can also just purely by the waiting time completely invert the populations. Yes, so how does now relate to the work by Jeremy and his collaborators? Well, if we take, for example, the optimized schedule here, and we keep it as is, but all we do is we introduce some waiting time here. So the schedule is nothing changed. We kind of, the waiting time we then also append to the total time. So this is literally exactly the same schedule, except you wait a little bit at some point. And depending on this waiting time, we can now plot the ground or the probabilities of ending up in the ground or excited state in the end of the anneal. And indeed, it kind of oscillates as a function of this waiting time, right? So the phase that the system picks up in these on each or either side of these transitions, they seem to be kind of very relevant to actually creating the ground state population that you would like. So our claim or discovery is that these optimal schedules, they do exploit this Landau-Zener-Stückelberg interference as like some sort of pumping mechanism to populate the first excited state, which then allows them to go fast to completely forget about the minimal gap and just go fast. And then they end up in the target ground state as they intended. So based off this, if we believe that this is the underlying mechanism that was discovered by the computer, we could now say, okay, let's just make this explicit. And instead of optimizing over all sorts of functions for the schedule, we choose an ansatz and maybe even an initialization that just explicitly incorporates or that explicitly respects this mechanism, right? So we propose to use schedules kind of like this, where you just have like a ramp, a wait, another ramp, a wait, and another ramp. It depends a little bit on the details how you encode this, but pretty much like if you just choose the ramps very small and the waiting time is also very small, this contains like the linear schedule. So if just linear ramps would be the optimal solution, with this ansatz you could still find it. But the nice thing about this ansatz is that you don't optimize over all functions, but like over functions with like very few parameters. Basically, you could kind of scale this up if you expect your problem to have more than one of these type of localized crossings, or if, for example, the pumping mechanism doesn't work quite as well, which is a topic I will get into in a little bit, then you could also just use several of these sweeping motions. Then obviously the parameter count goes up, but it's a small number of parameters, right? And it's kind of nice. And also it's interpretable, so we kind of know what each parameter is supposed to be doing. So if we want to do this, okay, the system needs to be coherent, because if we want to exploit the interference between mixed amplitudes, then if we have, if the system isn't coherent enough to do this, then it obviously doesn't get us anything. So it would also be interesting to look into how noise affects this now. And this is like a starting point to look actually what happens at if you decompose these type of schedules into just like waiting and ramping and then waiting for a little bit. You can actually kind of think of them as unitary gates with essentially 3 parameters. Like one wait time gives you a phase, the other wait time gives you the other phase, and then how fast you ramp gives you some rate at which you mix the populations. And you can decompose this into like 3 gates, like a wait gate, a ramp gate, and another wait gate. If you want to gate stuff, you will realize very quickly that if you could choose this R arbitrarily, this would be already like a universal gate, right? So because it's kind of, if R would be, if you could choose R arbitrarily by either going arbitrarily fast or arbitrarily slow, then this would just be like a Z rotation, an X rotation, and another Z rotation, which is just like a universal SU2 gate. However, in realistic scenarios, for all sorts of reasons, these populations, you won't be able to do it arbitrarily. One reason might be if you, for example, want to stick with the dynamics to the low energy subspace, the space spanned by instantaneous ground and excited state, then you don't want to go arbitrarily fast to avoid excitations to higher levels. So this kind of might limit the R that you can implement. But still, actually, if we look in or if we analyze what type of first excited state populations you can create, by Pn we denote the population in the first excited state that you have after let's say, n applications of one of these ramp and weight gates. If you apply then the next gate and look what happens to the population of the first excited state, you kind of get you just get an expression like this, right? Where Pn is the population that you start out with, and then Pn plus 1 is the next one after another gate. Thank you. And this expression kind of decomposes very nicely into like the first part, which we kind of can consider the classical part, and the quantum part, because this is the part where the phase matters, right? This is the part that kind of vanishes if there's decoherence. But independent of the R, or basically since the phase is tunable for different R's, we can now look what is like the next population that we can create. And if we plot those ranges for like an initial Pn, what would be the Pn plus 1? For each Pn we kind of have like a range by tuning the phases, and depending on how much population per sweep we can move around, let's say, we kind of get like ellipsoids or even circles like this. And this is kind of like a graphical intuition that even if this R is fixed, by just sufficiently many sweeps you can create any population you would like, right? And if you then in the last sweep you can also then with the last weight gate you can tune the phase. So this is basically like a universal gate set, even if the R isn't arbitrarily, or if you can choose the R's arbitrarily. And another nice point of this, that's it. With sufficiently many ramp and weight gates, you can create any population, right? And it gives us like a nice graphical way to interpret what happens to this mechanism when there's noise. So if we decompose the process into like this weight gate and treat it as a unitary channel, and the ramp gate and treat it as a unitary channel, and slap some noise channel in the middle with some noise rate mu, then we can look at the let's say the reachable sets after applying one gate and see that actually even just if it's only dephasing noise, for example, you cannot reach any arbitrary population anymore. So in the presence of noise, you cannot really you cannot invert the population between ground and steady state anymore as you please, which is kind of then detrimental to the working mechanism. And yeah, that was a rough summary of what I wanted to present today. So we identify like an explanation to why these optimized schedules work the way they do. And then it's like you sweep multiple times through the quantum phase transition and then use Landau-Zener-Stückelberg interference to populate the first excited state. And we can analyze this in like a simplified way just by looking at these ramp and weight type of schedules and gates. And they basically are very powerful. They allow you to prepare any state in the ground space that you'd like, but they're very sensitive to noise. And so some work in progress is we actually want to do this in a lab. So something I didn't have the time to get into anymore is we have simulations for like 2-level systems, and now we're pushing towards like an experimental realization. And okay, almost at time. Then I would like to thank my collaborators from Qilimanjaro, my supervisors Arthur and Marta and Arnau, and the original authors Jeremy, Matthias and Tamim, who agreed to kind of collaborate with us on this project. And also specifically Ramiro, because he's defending his PhD thesis today and is in the Netherlands and not here. So yeah, thank you very much.
Okay, we have time for questions. Let's go here. Thank you. Federico.
Hello. So I'm wondering if you have a more complex system that when you cross its phase transition in finite time, you will excite a lot of low-lying states, not only the first excited. And these states, even if your full dynamics is unitary, will decohere one with the other by scattering or some other mechanism. So how much do you think you can really exploit these going back and forth, keeping the coherence even if the low-lying states decohere one with respect to the other?
Yeah, that's a good question. So we haven't looked into the noise yet much deeper than this very simplified noise channel type of analysis. So yeah, like how it then scales up actually in a real device, that will be interesting to see.
Maybe you can speak afterwards.
Yeah. Thanks.
But even in a noise-free case, you will have Landau-Zener transitions to higher excited states, or
well, if we assume that you go sufficiently slow that you can neglect that. Depends a little bit, yeah.
That sounds a bit like Goldilocks ramping rate, exactly the right ramping rate.
Yeah, well, it kind of, it would require that it at least exists somewhere, and then the optimizer hopefully finds it, right? But looking at the simulation data by Jeremy, it actually seems to be working this way. So they actually don't have any excitations, like in the simulation at least, to higher levels.
Yeah, let's go to Kathy.
Yeah, so I actually have two questions. And I think Paul sort of asked the one, how generalizable do you think this is to all possible inputs that might be presented to a quantum annealer?
Possible inputs, you mean problem instances?
Yeah.
Yes, good question. Probably not all that much for various reasons. So, first of all, you kind of need to assume that the problem instance that you're given has only like this delocalized localization and then like the exponentially closing gap, but only one of them, right? If you have more than that, then it gets tricky. And there are problem instances where there are more than one of these closing gaps. So then you would, then this wouldn't work anymore. Although there are some also hard instances where you have kind of this type of gap profile, if you will. And then the other assumption is that the low energy subspace is fairly well separated from the high excitations in order to avoid the excitation to higher levels. And this then all limits the runtime, obviously, and how much you can exploit this. And on top of that, basically the runtime that you have now kind of depends on the first gap. So that gap, the gap at the phase transition, that gap for many problems also closes exponentially. So there's nothing to gain there, right? Then it wouldn't work. So it's.
But it sounds like it doesn't do any harm compared to like a linear schedule.
It shouldn't do any harm. No, it shouldn't do any harm. But whether you gain something though. We have to look into this, but it could easily be that this is, other than for the frustrated Eisenring, that you actually don't gain much.
And my other question was, you showed the diagram with the 7 and the 13 parameters. I only counted 5. I was.
Yes.
I counted one more than that.
Oh, you got 6?
but not 7.
7.
So the relevant parameters are essentially like how fast you take for the first ramp. The second, like the waiting time, the second ramp, another waiting time, and then the last ramp. Those are the 5 parameters, I assume that you counted. And the other parameters are the locations where you do the waiting, though, these 2. So we have 5 times and like, so 5 different times
and
then
2 heights.
Exactly, and 2 heights, yeah.
But there's not a total anneal time as well, so that would make 8.
No, that's not the total time. So in the simulations of where we applied this ansatz to like a 2-level system, we kind of exploited that the total anneal time is just the sum of these 5 times. And then kind of by introducing some Lagrange multiplier methods on that, or some Lagrange multiplier on the total anneal time, had the algorithm optimize both the schedule as well as the total anneal time in one go. A little bit up for debate if that's actually the smartest way of doing this. But the total anneal time would then just be the sum of all the 5 times.
Thank you.
We should probably move on now, so let's thank Matthias again. Thank you.